Today, let's talk about Gruber's algorithm. So, it's one of two pillars of the quantum algorithm, and usually it's called the searching algorithm. So there are many type of NP problem, but I'm not saying this is an NP problem, but it's a kind of a problem that has the same spirit of an NP problem. So which means that when you search something, you don't know how to find efficiently searching some item, right? So the item that you want to search could be at the end of the searching. Nobody knows, so nobody can really tell what's going on until you search every item. So people have been thought about many searching algorithms depending on the type of the item, type of the lists, but that's just it's not a deterministic algorithm. So Gruber thought about how to use the quantum circuit or quantum algorithm to find searching algorithm. So here's the problem. So it's not technically divided into computational problems and quantum circuit, but I'll try to do my best to write it out. So the computational problem is, suppose that we have a function that gives 0 and 1, depending on whether your query is equal to A or not A. So we want to search for A. So we know what A is, and but the thing is, we don't know what A is. So we have to find out what we are looking for. So it gives 0 when X is not A, and it gives 1 when X is A. So 1 out of 2 to the n. So suppose that our string is n-bit string. So 1 out of 2 to the n throw, or 1 out of 2 to the n tries, you will only get 1. So you are looking for that case. Once you find that value 1, you're done. Okay, so here is A. So not really a computational problem, but that's our goal. We want to find A, supposing that we know what f of x is. Okay? So what is quantum circuit? So we kind of assuming that we already implemented this function into Oracle. So our Oracle so I'm not saying actually quantum circuit here, but I'm just saying that there is an Oracle that could be inserted into a quantum circuit. And this is typically the same circuit, the same Oracle we have seen so far. So it's just y plus f of x. So which means that when you have an input register and output register, so input is n-bit string and output is just 1-bit string. Sorry, so 1 here. So then let's say y. So x and y is just the base state. So x is just 0, 1, 0, something like that, and y is 0 or 1. And when you put this into Oracle, the input string, input register doesn't change, the same string, but the output is changed to plus f of x. Okay? The same Oracle. So let's suppose that somehow we miraculously implemented this Oracle into a quantum circuit. So then what we do is, how do we find that A that gives the value of 1? So one way you can manipulate this is, let's not start with just random y. Let's make it into something special. So when you have the output register, this part, into Hadamard times 1, so it means minus state. Okay, so we have a minus state here. Then what happens? So the input state doesn't change, it's just x itself. But think about the case when you have x equals to A or not A. So if it's A, then you change the state from 0 to 1 and 1 to 0, right? So you interchange 0 and 1. So you get the minus sign in the minus state, right? Minus kept, right? So when x is not a, we don't do anything, right? Because the value of function is 0. So the minus cat is just minus cat, because 0 cat is 0 cat, 1 cat is 1 cat. We don't do anything because this is 0. So this is actually depending on the value of function, that if it's 1, the value of function is 1, then you get a minus. That's exactly when x is a, and plus 1 when x is not a. So let's put this out in front. So we get minus 1, the power of x, xn minus 1. We don't put the 1 here, because minus just minus 1. All right. So you see what I'm going. So instead of just applying the Hadamard, the oracle right away, so we're going to do something on this output register, and make it into. Let's pass it through the Hadamard gate after initializing at one cat state, and then so we're going to do something interesting here. So we're gonna define two unitary gate and one V and W. So let's define this V first. So V and W are both unitary gate acting on the n-qubit state. So it's a linear transformation on the Hilbert space of n-qubit states. And V is defined to be, so I only need to define what's happening when I apply to base state, right? So let's say x is a base state, and this is equals to minus 1 f of x, x, n. So it's the same thing. It doesn't change anything if x is not a, and it changes the sign when x is a. Okay. So you can see that actually follows from our settings here. So since it's harder to consider this type, although it's just definition, so we manipulated our output register to say this quantum oracle only manipulates the input register. So we just take this part out because the output register seems not affected by any quantum oracle for any inputs x. So we just take this out into a separate operator, V. Okay? And how does W defined? So we need to do a little bit definition here. So let's say V to be the superposition of all possible states. So just take the Hadamard gate on every single input register, input quantum of n qubits here. And this is, as we all know, superposition of all possible state with equal coefficient. So xn, and then we define W to be the following. So it sounds a little bit weird, but I'm not using the notation of the unitary gate into a specific mapping here. So I'm using the cat-bra notation here, bracket notation. No. Cat-bra, sorry, right? So cat-bra notation. So whenever you have, remember when we introduced the cat-bra or bracket or whatever, so we can think about this as a matrix, because the bra is the row matrix and the cat is the column matrix and bra is the row matrix. So you can multiply these together to get the matrix. And this one is identity matrix, identity operator. So basically this definition gives you whatever you do acting on the base state, you can just compute this as follows. So 2 psi x minus x. Okay. So these two are separate unitary gates, just linearly combined together. So you can act on this x cat separately and then combine together linearly. And what is this? So I'm saying that x is just the base state. I'm not saying it's just, it's not a linear combination of other states, just 0, 0, 1 or whatever. So when you do that, then, so we know that this cat state, the bra is the dual of that. So in fact, so when you take the dual of the cat dual of each cat, you take the bra, but you also have to take a conjugate of the coefficient, but these coefficients are always real number, so there's nothing to take a conjugate of. So it's just 1 over 2 n over 2 x from 0 to 2 to the n, and then bra. So let me change the notation here because I already used x as some kind of specific string. So nx, right? So I'm doing this. So I'm taking bracket of everything with x, right? So you see when you take the bracket, now this is the bracket of n string or n qubit state, right? So every bit of each bit digit must be the same in order to get 1. So otherwise, it's always 0. The bracket is 0 whenever your x and y as a string are not equal. So what you get is, so also, I shouldn't forget this identity operator. So minus x, right? So this part becomes, I forgot the 2, right? So there must be 2 here, twice. So, oh, okay, so I forgot this part. So basically, yeah, 2 is here. 2 is here, and also there is psi. Yeah, and then, yeah, so and then minus x, right? So what happens here? So among this 0 to 2 to the n minus 1, there is at least, I mean, exactly 1 state which is equals to x. So in that case, you get 1. So the only thing remains is the 2 over 2 to the n over 2. That number is the coefficient of psi. So 1 over 2 n over 2 minus 1. And we assume that n is equal to, bigger than or equal to 1. So you don't have to worry about negative sign in the exponent here. And psi, phi here, and minus xn. So if you really want to show that how the w is defined in the same way we define v, then this is the formula. So whenever you apply the base state x, this becomes, oh, sorry. So this is what where I started, right? So let me just write it down here. N over 2 minus 1 psi minus x. Okay, so this is our definition of w. Okay, so erase this part. So this is 2 over 2 n over 2. Okay, so now we define v and w, and let's think about how the Gruber algorithm works. So, so basically, since I defined the necessary things already, the basic procedure of the Gruber algorithm is applying this v and w successively. So, apply successively onto phi. Okay, so it's very easy to just preparing phi because you just initialize all the input state into 0 cat and then apply Hadamard for every single input qubit. And then what you do to use the Grover's algorithm is to apply v and w successively. So you can take this as a set, take this as a one unitary gate. So you don't want to apply v many times or w many times, but you always come with a pair. v, w, that's one iteration, and then another v, w, that's a second iteration, and so on. So the question is, how many times do I have to apply v, w? Or in the same way, when do I stop? When should I stop? And another question is, how do I know when I apply these VWs many times that I can get what I want? So I want A, right? How do I know? So here's the thing. Oh, where is it? Okay, so here's the thing. So let's think about V and W again. So what does VW do on the very two special qubits, the quantum states? So when I apply V onto the ket state A, right? So A is the special case. So yeah, at this moment, although I started the case when I introduced the question, so you should know what A is. You should know what you're searching for, right? But the question is, so it's a tricky question. So if you know what you're looking for, then you don't have to search for that item. But so yeah, so basically, so you can think of the situation like this. So you kind of prepare the oracle, which is determined by the existence of A. So there's some A that defines the function, the search function, but you don't know what A is, but you somehow manage to implement that as a quantum oracle. So without knowing what exactly A is, you have the oracle that you can query with, and also you have a classical function that you can query, ask the function whether the value at certain number x equals to 0 or 1. So if you get the 1, then you can find what A is, but it's very rare chance. So here again, so when I say V times A, so this A is not known, but there's some A, right? So the A, unique A, that determines a function, that's that A. Okay, so we kind of, without knowing what A is, but we know that we can, since we defined V in this way, so so we can know what happens when I apply V to A. So in that case, you might ask, okay, so without knowing A, how can I define V? But that's what this oracle says, right? So oracle actually gives V. Oracle is V. So we're not making V from nowhere. So we have made the oracle. That means we made the V. Okay? So that's a kind of a tricky part. So, but you have to make sure that this V is not made out of nowhere. It's made from this quantum oracle, because whatever you do on this quantum state is applying V. So we know, so it's not just theoretical unitary gate. It's actually real. Once you have a quantum oracle, you can see what happens. This. And by the definition, we know that this is minus V. Look at this. When x is A, it's minus A. So also, let's think about what happens to this. So when you apply V on the phi, the special quantum state we define that way, what happens? So it says when x is not A, it's same thing, but when x is A, minus, right? So, so you can say this way. So except for A, everything stays the same, but when A, at the ket A, your coefficient become minus, right? So all you have to do is just take the same thing, phi, and then take out twice of the coefficient of the ket A, right? 2 times of 2n over 2a. So that's the state, right? When you apply V to phi. So what we are doing here is we're taking n to be very large. So if n is not large, then there's no point of using Grover algorithm. Just use a classical computer, right? So n is very, very large. So 1 over 2 to the n over 2 is very, very small number. So you can almost ignore the coefficient here because it's almost 0. So you can imagine that this is almost equals to phi. Okay? So in a very loose sense, what V is doing is that it's kind of preserving a phi, but flipping A. And also, let's talk about W. So what does W do on A? So WA is, since we have a definition here, where we're here, so let's see, 2 phi ket bra A minus A, right? So this one, we already computed here. So it's 2 over to n over 2 v minus a, right? So you can see also that this coefficient is very small. So, so this is almost equal to minus a, right? And what happens to this? So when you apply this, then by definition here, you get v minus v. Now, when you do this, it becomes 1 because that's the same thing, right? So it's just v, okay? So if you just look at v and w not rigorously, then this seems almost the same thing because you see w is preserving a to not preserving, it's flipping a to minus a, preserving phi to phi, and that's same for the operator v. But, well, if you ignore this part, then there's nothing to do with. So it's not, the Grover algorithm actually depends on not ignoring this part, but I'm just showing you that the idea about it, why there's v and w here. So let's think about more rigorously, not thinking about this approximated state. So let's say, so I'm going to use the vector notation now. So when I say vector, you have to use the arrow for best visualization. So let's say I depict my cat A as a vector with this arrow, and this is the origin here. And what v does is it actually preserves everything else, right? Except for A, everything is preserved. Where is it? So everything is preserved, right? So there must be, so in this case, what is the dimension of the Hilbert space? It's n-dimensional vector space. So there are one vector A pointing direction of A, and the other n-1 linear independent vectors spans the n-1 subspace of the Hilbert space. So let's say I depict all the n-1 dimensional subspace, which is orthogonal to this vector, as a perp. Okay? So I'm not saying this is a single vector. I'm just representing this as a some vector inside of the hyperplane of this vector, orthogonal to this vector. Okay? So you can depict that as if this Hilbert space is 3-dimensional, then this is a surface. But I'm saying that n is very large, so it's whatever I do to best visualize, it will not be the best shot. So I'm just writing as the line here. So these are perpendicular, which means that if I take any other vectors which is non-linearly which is linearly independent to A, then it's going to be the orthogonal, right? So what does v do? So let's say if I take any vector or any quantum state, then this is some linear combination of some A times coefficient plus some linear combination in the orthogonal state, right? So v actually flips this A to the minus A, but not doing anything, just stays the same thing for any vector orthogonal to A. So when I apply v, it's actually flipping across this hyperplane, right? Because let's see, C0A plus C1A perp becomes, so this part is consisting all the linear combination of x which is not equals to A, so therefore the same thing. But this part becomes minus, right? So you can draw this situation as a reflection across this hyperplane where the A perp lies on. And then what happens to W? What about W? So W is also reflection. Why? So W is a reflection across, so this is V, so not V psi, and so this is what V does, and W is also reflection because it's now preserving phi, the one special quantum state. And what else does, what does it do on the rest of the part? So it's doing a something opposite here. So let's say, so phi is not a base state, but it is a quantum state. So just consider it as one vector, and then consider all the perpendicular vector to this quantum state. So again, the same idea here, but the phi, only difference is the phi is some superposition of base states, like specific superposition of base states, where we defined here. And you can think of all the perpendicular states, that state. And what it does is, in this case, actually something opposite. So in this case, we are actually reflecting across the hyperplane orthogonal to A, but in this case, it's reflecting, let's say if this is psi, over this phi, W psi. See what I mean? So it's also reflection. So you can see. So it's in 2 dimension, it's clear. So in 3 dimension, it's kind of, what do I say? So it's whatever. So in the 3 dimension, let's say if I have this, so this is phi, and let's say this is phi per 1. Let's say there are 2 bases to this 2, let's say this way. So and then so let's see, this is my psi. So let's say if I take the projection onto the hyperplane here, let's say psi perp, then what W do is taking this psi into here, where if I take the projection here, it's going to be minus psi perp. Okay, so that's why I'm actually thinking about the correct word instead of reflection. So in this case, it's actually reflecting across the hypersurface. But here, it's a reflection, but how do I say? It's kind of a antipodal point. You're mapping into antipodal point, right? You want to stay this axis the same, the direction to this axis the same, but all the other directions are just inverted. Okay, but let's call this also reflection. Okay, so having this idea, what does applying VW successfully means? Let's just apply VW once, what happens, and see what happens. So, does it make sense so far, what we're talking about? Definition of V and W and also the reflection part? Because that's the entire idea about the Grover's algorithm. All right, so here's the picture. So you have A, and you have A perp. And what is the cat bra of phi and A? It's 1 over n over 2. 1 over 2 to the power n over 2, right? And this is very, very small. It's not 0, it's just small. And we say when you take the bracket or inner product, you get the angle between 2 vectors. So what do we mean by angle between these 2 quantum states? Well, it doesn't really have a physical meaning, but mathematically you can think about as an angle between any vectors, and quantum state is a vector as a mathematical object, so we can think about the angle between quantum state. So let's think about this situation, and since the inner product is almost equals to 0, that means you can say that this A, and somewhere there is phi, and these 2 vectors are almost perpendicular, but not perpendicular, exactly perpendicular, not exactly perpendicular. So I want to set this angle theta here, not the angle between A and phi, it's the angle between phi and A perp. You can take any A perp here. So A perp is just a vector that is on the hyperplane orthogonal to A. Okay, you can take any vector to get the same angle here. So then what is this inner product? So it's always cosine of angle between, right? So it's cosine of pi over 2 minus zeta. So reason why we don't have, so this is the usual formula you learn in the multivariable calculus. And the reason why you don't have the norm of phi and a is that the phi and a is already normalized, right? So it always have the size 1, strength 1. So we know that this is equals to sine zeta, right? So when sine zeta, when zeta is very small, or really, really small, close to 0, and we know that sine theta is almost equals to just zeta, because the graph of the function sine x is almost equals to x when x is very small. So from here, what we can conclude is zeta is just almost same as this value, right? So of course there is an error, but the error is almost negligible. So anyway, let's apply v and w. Let's apply v first. What did we say about v? So v is reflecting across the hyperplane, right? So when I apply v on here, so remember that we are applying vw on phi, okay? So phi is the starting state. Let's apply v to get this. It's the same angle across this A perp. And then let's apply what? W. So what does W do? W reflects across this line, the vector phi. So it's going to reflect on this axis, So it's going to go this way. So you see, after one reflection, I have now 2 theta angle difference. But with these 2 theta angle, I'm reflecting across this line. So I get 2 theta here. So that's why where I get WV phi. Okay? So I was here, right? I was here in the beginning. And when I apply WV, I have 2 theta more difference between the angle between A perp and our new quantum state. So what happens when I do this again? What happens when I do this again? So let's, should I make it again? So here, let's draw this A perp, A, and phi, and here VW phi. Let's call it phi 0 and phi 1. Okay, so I'm applying WV on phi 1, right? So let's apply V first. So V is reflecting across this, right? So this is V phi 1, right? So this was theta, this was 2 theta, and how much is this? 3 theta, yes. And then what do? Applying W, right, on here. So it's going to reflect around this phi. So let's say this is VW phi 1. So how much is this? Yeah, 2 theta, right? Because it has to be 4 theta in total. So what do I do? Well, what did I make? When I get to the second application of W and V. So I'm increasing my theta, the degree, by 2 theta every time, right? So what's my goal? Where do I want to go? So I want to make the angle difference, I want to make this vector almost in the same parallel direction to A. I want to make it that way. So again, I don't know what A is, but I can give what I do know is that how much my theta is, because this is approximately this much, right? So if I want to make this angle between the A perp and the state that I get after successive application of WV to be almost pi over 2, which is perpendicular, then I know that our quantum state is almost parallel to A. So then it must be A. So in that case, without knowing what A is, we can query that state into our quantum oracle or just classical function to whether that state is actually what we want, is actually A, whether it's actually A. Because we know by the outputs 0 or 1 that is whether our string that we inputted in here is equals to A or not. So anyway, so let me summarize here. So after, let's say, apply WVK times, our angle becomes WVK times the angle between what? A perp and this becomes 2k plus 1 zeta, right? So we want our final state, the final state to be perpendicular to A, so let's call this VK, this V is parallel. So when it's parallel, actually it's the same thing because everything is normalized. To the original A. So again, we don't know what A is. We just expect that whatever we get is same as A. So how many times do you have to apply this VW in order to get the perpendicular angle, pi over 2? So we want 2k plus 1 zeta to be pi over 2. So we cannot get exactly pi over 2, just having an expectation here. And so since zeta is very small, so we mean if you want to get this much, then k must be really large. That means 2k plus 1 is almost equal to 2k. So this 2k theta is approximately pi over 2. And zeta is approximately, it's not zeta, k, we want k. So k approximately pi over 2, 2 zeta over 1, right? So it's pi over 4 times, so zeta, what did I say about the zeta? Zeta is this much, approximately. So it's 2n over 2. Okay, so as I said, n is a very large number. So 2 to the n over 2 is still a large number, right? But it's better than applying, better than query the function 2 to the n times, because the number of queries, number of computation, which is k, is down to the square root of the total number of the items in the list, right? But although there is some small coefficient here, but that's negligible because this one is very large, right? So what's the conclusion? So this is not exact number, but if you apply this much application of V and W, and then you ask oracle or functions whether this quantum state, the final quantum state, is the one that we are searching for, just by looking at the value of function, it may or may not have 0 or 1, right? But in that case, if you get 1, then you found that string A. If you don't get the 1, then you take a slight modification of your application and then do it again and again. It has a better chance. So there is no strict percentage how much chance that you get the actual A, but that's better than just brute force searching what A is from 0 to 2 to the n minus 1. Just searching for those cases first, applying this much. So if this kind of k does, so even though this is not an integer anymore, right? So you just try out the k which is near this number, right? and then you might get the value 1 after applying this. So that's a better chance than just doing from 0 to 2 to the n minus 1. So let me finalize this one. So try out integer k near that number and query psi k into the function to see if psi k, so this psi k is n-bit string, final quantum base state that we get after applying this, so if this is equals to A. So not deterministic, but kind of better than occurring 2 to the n times. That's the idea. So let's say you have n equals to 10. Then in principle, in order to find the string deterministically, we need to query 10 to the 10 times, right? But in this Gruber algorithm, it basically says that you can do 10 to the 5 querying the function, or 10 to the 5 computational computation, or some integer multiple of 10 to the 5 computations in order to find supposedly the right string A. So that's the idea of a Grover algorithm. Make sense? There are a few more things that I want to cover, but before I move on, so just make sure that how you construct V and W. I want to see how you guys are in understanding this, because so frankly, I haven't seen how Gruber algorithm in real life, if there is a quantum computer, could be implemented efficiently. I don't know how this is actually efficient. So I don't know exactly where this Gruber algorithm could be applied, but because, for instance, in a Shor's algorithm, the best application is the breaking code RSA encryption. But in that case, it's kind of feasible. So if it's RSA 256, that means you could have a quantum computer with at least qubit number 256, then you can implement RSA breaking, right? But in the Gruber's algorithm, it's kind of different story. So, so even though you have, let's say, the string whose bits are 256, that means, in principle, in classical computer, you should query the function 2 to the power of 256, which is really large and it's impossible. But in quantum circuit, in a Gruber algorithm, you still need to query 2 to the power of 128, right? That's also large. So I don't know how this is efficiently implemented in the quantum computer, and even if it's implemented, how it's really efficient, how it genuinely solved the problem of searching problem, right? So there's some question mark that I have, but at least I want you guys understand what's the idea of original Gruber's algorithm. Maybe people try to improve the Gruber's algorithm, which I don't know. But that's the original thought. Any questions? Just have a, not, even if not a questions, just, yeah, yes.
What happens the result is doesn't match to our target A?
Oh, okay. So if it's not, so once you have whatever that psi k is, you take the measurement and then you query the function with that string, and there are many chances. So again, so this psi k is a superposition. Ket psi k is a superposed state of many quantum states, right? So having a perpendicular to a perp and having a parallel to A, which does not mean that it's actually A, it has a large coefficient. The size of a coefficient of A is getting larger and larger, right? So if you take the measurement of ket psi k, phi k, then it has a larger chance to obtain A, right? So that's the whole idea. So if you take the one measurement, you didn't get the, and then you query that string into your function and you didn't get 1, then you shouldn't change your k. You have to take the measurement again, because that could result of the small chance that you didn't get this A, which has a large coefficient, but with a small chance, you could have measured another quantum state which has a smaller coefficient. So you do it, you do the measurement of psi k again and again, which means that every time you want to measure psi k, you have to make psi k again from beginning, applying the wvk times again. But don't just change k right away. Just take the measurement sufficiently many times. And if it fails, even if it fails, then you want to change k slightly, because this is not even integer. So you have a large possibility, large range of possibility to try the actual k that gives you the right answer. So just change the number of application of VW and then do it again, like taking measurement several times, and then if this not works, then change k and so on. So how many times do I have to do this? Well, we don't know, but the idea is that how many times you do, it's actually better than trying 2 to the n times, right? Yeah. So I think Yen's question was actually have a good point. So so when I say this psi k, so this psi k is the measurement outcome of this state. So psi k ket psi k is not a base state. It's a superposed of several base states, or exactly 2 to the n number of base states, because it started from the superposition of 2 to the n base states. So there's no base state is disappearing, right? Everything is survived, but the only changing is the coefficient. The size of coefficient changes. More and more we get to the state which is parallel to a perp, the coefficient of this base state inside of the psi k gets larger and larger. So they get higher and higher chances to observe this one, right? So I'm saying that psi k is the measurement outcome, not the exactly state, because there's no meaning of, there's no point, right? You cannot have exactly one base state in your quantum state. Any other questions? Yes.
This one is searching algorithm.
Yes.
So I don't know why this is considered as the searching algorithm. Because effect is unknown for us for this problem.
Right. So A is not known. We don't know what A is, but we assume that the searching function f is given. So, okay, so I think I started from a very vague point. So our computational problem is to find A when we are provided with the function f, which is supposedly called the searching function. It's called searching function because it only gives 0 and 1, true, false, based on our inputs. Okay, so it gives you whether your input is the right one, the right search, or the one that you really want to search or not, right? So I think searching is kind of so I think you can think about this situation. So here is 0, 1, 2, up to 2 to the n minus 1. So let's say you have a present box hidden in one of these, right? So you have a present hidden in number 2. You want to find the present box, where the present box is, right? So that's kind of a searching, right? So every time, so whatever your algorithm is, if the situation is the worst case scenario, then your present is found at the end, right? So the only way you can find where the present is to open up all these boxes, right? So that's kind of a searching. So when you have a present, you get 1. And all the other cases, you get 0. That's why it's called searching function. So this function is given without knowing where the present is, right? That's A. This number A, this is A. So that's where we start. And also, it's kind of assuming that miraculously you implemented this search function into a quantum oracle. Or maybe the quantum oracle itself is a searching function. We don't know. But if we have this, how can we find out what A is? Where do we find, I mean, without searching all possible cases, how do we know where the where my present is? That's why it's called searching problem, searching algorithm.
Concern was to think that we are assuming that x exists without seeing every 2 to the n minus 1 and 2 to the n boxes at all. But isn't that what we want to implement? 한국어로
네.
그러니까 fx 자체가 2의 n제곱권을 안 돌고도 저 FA를 찾을 수 있다라는 얘기인 걸로 보이는데.
네.
근데 이 알고리즘, 글로벌 알고리즘 자체가 저기 1을 만드는 어떤 A를 찾자라는.
그렇죠.
그런데 fx가 존재한다고 가정하는 것부터가.
그러니까 fx가 존재하는데 A가 뭔지는 모르는 거예요. 자, 선물 박스가 있는데 열어보면 알아요.
그 열어보는 게 fx인 거고.
그렇죠. 열어보는 게 쿼리한 거예요. 근데 어디 있는지는 몰라. 예. 근데 이제 문제는 열어보는 거를 할 수 있으려면 그러니까 우리가 열어보는 행위를 이제 어디다가 이제 임플레멘테이션을 시키려면은 고정 컴퓨터든 양적 컴퓨터든 그러면 어디 있는지 알아야 되지 않느냐라고 생각할 수 있잖아요. 애초에 그냥 프로그램을 그렇게 짜려면은 어디 있는지 알아야 내가 이거 맞다 아니다 알 수 있지 않느냐. 그러니까 일단은 그거는 해결됐다고 가정을 하는 거예요. 그러니까 양적 컴퓨팅 알고리즘에서 대부분 사람들이 궁금해하는 것 중에 하나가 임플레멘테이션이 돼 있으면 이미 알고 있는 거 아니냐. 그러니까 사실 똑같아요. 버른스타인 알고리즘, 사이먼 알고리즘 모두 다 그냥 문제 자체가 임플레멘테이션이 돼 있다. 그렇지만 그 어떻게 작동하는지는 모른다. 히든 베리어블, 그러니까 히든은 모른다라고 가정을 하는 건데 어떻게 히든을 모르는데 임플레멘테이션이 돼 있을 수 있냐 이렇게 질문을 하면은 사실 이제 문제가 성립이 안 하거든요.
EX를 정할 때 숫자 이게 이렇게 박스가 있는데 그 중에서 하나를 그냥 랜덤하게 정해가지고 FX를 할 수도 있잖아요.
그렇죠. 랜덤하게 정할 수 있는데 이제 어쨌든 이게 랜덤이 맨날 바뀔 수는 없잖아요. 하나는 정해져 있어야 될 거 아니에요. 거리 할 때마다 랜덤 그 박스가 바뀌면 안 되잖아요. 정해져 있는 거잖아요.
이제 한번 풀 때마다 한번 랜덤을 한번 늘려가지고 FX를 정한다는 게.
아니야, 그러니까 이제 내가 쿼리를 어떻게 해도 내가 이거 1번 박스를 오픈을 했어요. 아니었어요. 근데 다음에 1번 또 열었더니 1번 박스에 있었어요. 이렇게 바뀌면 안 된다는 거죠. 선물이 어디 있는지는 정해져 있어야 된다. 근데 선물이 어디 정해져 있는데 어떻게 우리가 이거를 모를 수 있느냐라고 질문할 수 있잖아요. 근본적으로 그냥 이렇게 선물 박스가 딱 정해져 있는데 이제 예를 들어서 선물 박스를 누가 놨어. 내 눈앞에 있어. 눈앞에 있는 게 누군가는 세팅을 했을 거 아니에요. 누군가는 선물 박스에 선물을 넣었을 거 아니에요. 넣은 사람은 알잖아. 넣은 사람한테 물어보면 되는 거 아니냐 이렇게 얘기할 수 있잖아요. 왜 우리가 이걸 근본적으로 제일 쉬운 방법은 노는 사람이 있으니까 노는 사람한테 물어보면 되지. 이렇게 생각하면은 이제 문제 상황이랑 조금 다른 얘기가 되는 거예요. All right, so I'm going to finish off with giving you an idea how to implement this thing. So again, V is the quantum oracle. Okay, so we don't have to worry about V, although we can still implement V if you want to trick some things. Like if you know what A is, then you can find what V is. You can actually make V, but let's concentrate on W. So instead of V, let's think about W. Instead of W, let's think about minus W. So this is 1 minus 2 times VB, get bra here. And since these ones are the Hadamard gate, constructed by Hadamard gate, what we can do is change this into this. So you can see that the 1 is preserved when after applying Hadamard gate twice. So you have this is the unitary gate acting on n-qubit state. So this can be considered as applying Hadamard gate and then applying this oracle, this unitary gate, and then Hadamard gate again. Okay, so in the one case, there's nothing going on because you're applying twice Hadamard gate. And then, what does this do? Think about this case. So it says if the quantum state you're applying onto this unitary gate, that you're passing on to this unitary gate, is not 0, which means that every bit is not 0, then it's preserved. Because when you have this is 0 unless you had 0, 0, 0, 0, 0, right? So only when input state is 0, 0, 0, 0, 0, that has change of your sign. So this is exactly x goes to x if x is not 0, and only 0 goes to minus 0. So that's when x equals to 0, right? So how do you make this? How do we do this? So let's invert everything. Let's invert 0 to 1 and 1 to 0. So let's try to think of this way. So if you want to invert things, then you can apply the X gate on every input register. Right? So Xn means that you have applied X gate on every input register. And what does this part has to be? So in this case, this one, so again, 0 and 1, the role of 0 and 1 are inverted. So this one is a unitary gate that this x goes to x if x is not equals to 1, 1, 1, 1, 1, 1, which means that it's 2 to the n minus 1, right? That's the only case you have 2 to the n minus 1, which is that 1, 1, 1, 1, goes to minus of 2 to the n minus 1, right? So let's invert this thing. So this unitary gate must be something that maps these quantum state into these. So what is it? Let's say we have n equals to 6. Okay? 4, 5, 6. Oh, 5, sorry, 5. This is the case. This is what we want. It's 6. Yeah, 6 is right. Yeah, 6. Okay. So what happened? What is this? So this is the multi-controlled gate. So we talked about CNOT gate a long time ago. CNOT only have one controlled gate. This has several controlled gates. So this has 5 control gate and target gate. Targets, I'm sorry, not gates. So 5 controlled qubit and 1 target qubit, right? So total you have 6. So number of qubit is 6. And this activated, this control gate activated only when you have 1, 1, 1, 1, 1 on the above 5 qubits, right? And also when the target qubit is state 0, and when it's cat 0, it doesn't do anything because it's a Z gate. So it only when cat is the quantum state is cat 1, it changes the sign to minus cat 1, right? So only when you have 1, 1, 1, 1, 1, 1 cat state, it changes the sign into minus sign, right? So this is called C5Z. So C means C to the upper script, it means the number of control gate, control qubit. So what we want here is Cn minus 1Z. It doesn't matter where the control gate is, we just do it, put it anywhere. But when you want to draw it, this is the best picture. Just put the control qubit above the target qubit. It's the best idea here. So how do we make this control qubit? I mean, the multi-control gate. So this is how you can do it. Maybe, let's see. I need to draw a few more lines. So let me try my best here. So this is 5. You have 5 controlled qubit. So you need to add 3 more. So it's one more than the divider of this number of control gates. So 5 over 2 is 2.5. So you get 2 and plus 1. So right. So you get 3 more auxiliary gate qubits and put 1, 2, 3, 4, 5. And then at the end, you get the final target qubit. And so this is not the only way you can make this multi-control qubit, but this is one of this. And let's see. We have here, we have here, and we have, oh, sorry, here, and here. Okay, so this multi-control qubit can be implemented as a successive application of 2 CC NOT gates. So this has a 2 controlled gate. Okay, so this is called sometimes CC NOT. So because we have a 2 C's controlled. You see why it makes sense? So let's see. What happens when you have, let's see, we have 1, 1, 1, 1, 1, 1. So let's see if we can get the controlled gate here, minus sign here. So since we have, let's see, so I think it has to be initialized into 0. Okay, so since we have 1, 1 here, so these 2 control gate are activated. So this one is activated. So this plus sign is the X gate. So it's another notation for X gate. And this is activated. So 0 cat is becoming 1 cat here. So now 1, 1 is activated. So this one now turns to 1. And 1, 1 is activating this. And therefore 0 becomes 1. And therefore 1, 1 is activating Z here. Okay? And the next step is actually reverting to the original state, because so 0, 0, 0 is now turned into 1, 1, 1. So there has to be the reversing procedure to make it into 0, 0, 0 again. So let's say we have, how many? 0. So this one is 0. So instead of 1, 1, 1, 1, 1, I have 1, 0 here. Then what happens? So this is not activated, right? Because one of the control qubit is 0, so the X gate is here is not activated. So still this is 0. So because this is 0, even though this is 1, this is not activated, not activated. Therefore, this is not activated, right? Even though it's 1 here, right? Okay, so that's how it works. So if you take another example, then you can see that except for 1, 1, 1, 1, 1, we don't have an activation of Z. Or actually, the activation of Z have an effect whenever we have 1 here. Okay. So now the question is, how do you get this CC0 gate? And that's kind of easy. And oh, there's two things here. The two things we have to consider. The one is how to make CC0, and another is how to make CCZ. Okay, so CC0 I have to. I'll explain next time because I forgot to take a note about this one. So you have to do a little bit of work to do this. But CCZ is a little bit easier. So this is how you can make CCZ. Sorry, so it has to be box here. So there are 5 successive C0 or C something gate here. So we have C square root of Z gate. What is square root of Z? So Z is 1 minus 1, right? Square root of Z is, consider this as e to the pi I, right? So it's 1, 0, 0, e to the pi I over 2. So you can make this gate. So this is, what is it called? I forgot its name, T or S gate. So you can make this gate, right? And also you can make, if you have any unitary gate, you can implement physically the C unitary gate. So these are the C unitary gate given with the square root of Z gate here. So you see this, you have to understand why this makes sense. Okay, so you can just plug in all the possible cases. Let's say we have 1, 1. So that means you have to be activated. So what happens? So it's 1 X activated here. So because it's 1, you are activating X gate, so it becomes 0. So this is not activated. But then 0, so since because it's 1, you're activating X gate, and 0 becomes 1, and then you activate this. So you have activation of these 2 gates when you have 1, 1. So therefore, you're activating Z. So now let's going back to another case, 0, 1. So you can try out other cases too, but I'll do this one. And 0 does not activate this one, and also not this one. So 1 activates it, and 1 activates, so 0 and not activating this, and 1 activating this, and I think something must be the dual of this. Let me make a research again and then try to change my comment. So I think these must be the same thing. I think this must be somehow dual of this unitary gate, which means the inverse of the unitary gate. So it has to be identity again. So let me make sure that after I find out, searching the book, and then I'll tell you this more exactly in the next time. So anyway, this kind of quantum circuit can implement CCZ gate, and also CC0 gate, similarly, not the same way, is constructed. So having this CC0 gate, you can make multiple controlled gate. So overall, you see, this is not the only thing you need. You have to have this Hadamard and X gate just to make W, right? And V is there.